The proposed SECRM-2D model is a two-dimensional state space representation for a vehicle control system that aims to optimize the efficiency and safety of the vehicle's movement. It utilizes a statewise constrained Markov decision process, SCMDP, to formalize the control problem as an optimization issue. The state space includes various features such as the ego vehicle's distance from the start of the current section, speed, previous acceleration, section index, lane index, lateral speed, and a Boolean map indicating whether a lane is part of the ego vehicle's route. Other vehicles within a fixed scan radius are also considered, with their state representations consisting of longitudinal distance, speed, and acceleration. The action space consists of a two-tuple, alpha, L, where alpha is an acceleration action and L is a lane change action. The acceleration action is continuous and subject to state-wise constraints, while the lane change action is discrete and subject to constraints that prevent unsafe changes. The reward function is a weighted sum of four terms: efficiency, comfort, route following, and safety. The efficiency term penalizes the difference between the current speed and the target speed, which is determined by the safety constraints and the speed limit. Comfort is measured as the square of the jerk of the ego vehicle, with a penalty applied for higher jerk values. Route following is enforced through a cost function that discourages the use of lanes not part of the route. Safety constraints are also enforced through cost functions, ensuring that the vehicle maintains a safe gap and adheres to the speed limit. The objective of the agent is to find a feasible policy that maximizes the cumulative discounted reward, which is defined as the sum of the rewards over an infinite time horizon, discounted by a factor of gamma at each time step. This setup allows the agent to balance between improving efficiency through discretionary lane changes and minimizing the risk of missing its route, depending on the value of gamma. The proposed framework for autonomous vehicles aims to optimize both discretionary and mandatory lane changes by balancing two aspects: switching to a lane with a higher target speed and following the intended route. The deep deterministic policy gradient algorithm is utilized for training, which is suitable for continuous action spaces. The algorithm updates both the critic and actor networks to maximize the expected cumulative discounted reward. The hybrid learning approach considers the current traffic environment to calculate the maximal safe target speed, deciding on longitudinal acceleration and lateral decisions. The safety-aware autonomous vehicle control system is developed by enforcing safety through action constraints rather than a safety term in the reward function. The system is trained using DDPG in two environments: a simple loop network and a network based on a real-world freeway. The loop network focuses on efficiency, comfort, and discretionary lane changing, while the QEW network evaluates route-following tasks alongside efficiency and comfort. Uncontrolled vehicles are modeled using the Krauss car-following model and the SL2015 lane change model. The training configuration, including parameters like discount factor, simulation time step, and learning rates, is detailed. The convergence of efficiency and comfort rewards during training is demonstrated, indicating the system learns to balance safety and efficiency. The long-term longitudinal behavior of a collection of vehicles is analyzed, showing the formation of platoons at the same speed as the lead vehicle. The framework's ability to optimize lane changes and ensure safety is showcased through the use of realistic traffic scenarios in the Sumo simulator. The stability of the equilibrium point, G*operator, V*operator, for the system is proven to be asymptotically stable through Jacobian matrix analysis, where eigenvalues have norm less than 1 when W greater than 0, ensuring stability. In the case where W equals 0, complex eigenvalues indicate instability. The removal of simplifying assumptions necessitates an initial speedup period or a speed limit to ensure the follower can catch up with the leader. This has qualitative implications for SECRM-2D platoon formation, expecting a well-trained model to form a platoon with a common velocity and intervehicle gaps described by previously obtained formulas, as confirmed by empirical tests in Figure 10. However, if speed limits are applied, it may not be possible for a follower to catch up, leading to the formation of multiple platoons. The SECRM-2D model is introduced to improve safety in autonomous driving by incorporating hard analytic safety constraints on acceleration and lane change actions. The model is evaluated in 3 scenarios: bypassing, emergency braking, and merging. In the bypassing scenario, SECRM-2D generalizes to unseen configurations, achieving 0% crash rate and outperforming baselines in efficiency and comfort. In emergency braking, SECRM-2D also achieves a 0% crash rate, emphasizing its safety. The merging scenario demonstrates the model's ability to generalize to different route-following scenarios without retraining. The results highlight the advantages of SECRM-2D over existing RLBA-SED controllers, particularly in safety, efficiency, comfort, and route following. The model's performance is attributed to its ability to balance safety, efficiency, and comfort, making it a promising approach for autonomous driving. In the context of a platoon of SECRM-2D vehicles moving at a constant speed, the long-term equilibrium is examined. The inter-vehicle gaps are expressed precisely in terms of speed and vehicle configuration. This analysis serves as a foundation for understanding the stability of the follower with a constant speed leader system. The stability analysis reveals that the eigenvalues of the Jacobian matrix at the equilibrium point satisfy lambda plus or minus less than 1 whenever W greater than 0, which is crucial for ensuring safe and efficient traffic flow. The research team's expertise in reinforcement learning and intelligent transportation systems, including car-following models and lane-changing strategies, significantly contributes to this study. The findings emphasize the importance of integrating artificial intelligence and transportation engineering principles to improve urban freeway operations. By applying these principles, the potential for enhanced traffic flow and reduced congestion can be achieved. The research team's work highlights the significance of considering both vehicle speed and configuration in maintaining optimal inter-vehicle gaps, thereby promoting smoother traffic flow and reducing the risk of accidents. This study's outcomes underscore the importance of interdisciplinary collaboration between AI researchers and transportation engineers. It demonstrates how insights from reinforcement learning can be applied to real-world problems, such as optimizing traffic flow on urban freeways. As cities continue to grow and traffic congestion becomes increasingly problematic, the integration of AI and transportation engineering may offer valuable solutions to enhance safety and efficiency in urban transportation systems.